It says Madison received $10,000 in gift money when she graduated from college. That is one heck of a gift. It'd be really nice to receive that. It says she deposits the money into an account that pays 5% compound interest annually. Okay, so you see interest, and you should see something that you are at least somewhat familiar with, right? In previous units, we've talked about very simple interest, and we didn't really get into a whole lot, but we got into some just basic, really simple interest stuff. I think when we were doing systems of equations. So compound interest is different. Okay, so we have a little bit of knowledge about the concepts here, but we do need to kind of look at how compounding interest works a little bit different than simple interest. Okay, so that being said, I want you guys to please answer 1, A, and B, and then fill in the table on problem 2. Okay. So again, if you would do all of problem 1 and all of problem 2 together with your partners, go ahead. All right, guys, so A wants me to calculate the earned interest for the first year. So if I have a 5% interest rate and I'm investing $10,000 up front, how much interest did I earn in the first year? $500, right? I do 0.05 because that would be 5% times 10,000, and I would get an interest, or the interest of $500. B asks a little bit of a different question, though. How much money was in the account after the first year? $10,500. So am I safe to assume that I earned $500 in interest every single year?
Yeah. Around that. No. Maybe. No. No, actually, because the amount increases.
Okay, so is this a simple interest problem? No. If it was, I would earn $500 in interest every single year, blah, 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 game over, right? That is simple interest. This is compound interest. So compound interest means after I gain this new amount, now I take 5% interest on the new amount. So when I take 5% interest on the $10,500, and then we can start filling in our chart here, it looks like the interest after, for the second year would be $525. So that's how I get up to $11,025. And then I keep going on and on and on and on and on. Yes, sir?
Was doing this very, very boring, like this part, because multiplying by 0.05 and adding it was a very long process?
It was a very long process. And so let me ask you, would you like to continue doing this process, say if we wanted to know how much money was in the account in year 20? Yeah, neither would I. Okay. What's an alternative option? What? Yeah, what have we always done in the past when we find a pattern but we don't want to have to continue writing tables? We write equations, right? We write equations. So we're going to do the same thing here, except it's now going to be an exponential equation and not a linear equation, right? Because the rate of change here is not the same. It's not just plus 500, plus 500, plus 500. This is not a linear equation. This is going to be exponential. So what is a key part of every exponential function? What's the important, or the very, very important part? Yeah, the growth factor. Remember that? That we talked about from last night's homework? Okay, so the growth factor is very, very important, and that's what the couple questions at the top of the next page ask you. So I want you to answer 3 and 4 together with your groups at the top of the next page. Go ahead. Okay, so I saw a lot of answers of 0.05. What does multiplying by 0.05 give me? The interest. Not the new amount in the bank. Nope. But you have to have a common multiple, right? A common growth factor. That's all I'm giving you. I'm going to try to lead you in the right direction, okay? Since we're kind of struggling here. If I only have the interest, if I only multiply by 0.05, What am I missing?
The total. Or like
The coefficient.
what is it? The initial
No, not the
value.
coefficient. I'm saying
What?
The initial value.
The initial value, right? Because after year 1, I should have the initial value plus the interest. So what could I multiply by if I only wanted the initial values each time?
What?
So I have 10,000.
One.
1.
2.
That's a novel idea. If I multiply by 1, I get the initial value.
You said you wanted the initial value.
You're right.
I am?
Yes. I was saying you're right. Yeah, okay. So if I want the initial value, I need to multiply by 1. If I want the interest, I need to multiply by 0.05. So what should my constant growth factor be?
One time.
That would be.
Come on, I thought we were going in the right direction. What? 1.05.
Ooh, I knew it. I got that right.
It does. Where's my stylus? Okay, so we identify our constant growth factor, and guys, it is always that way, okay? For any interest problem, as long as the values are increasing, for any interest problem, it's that way. Because if you only multiply by the interest problem, or by the interest rate, you only get the interest. Okay, so I need the value plus the interest. So here my constant growth factor is going to be 1.05. Okay? All right, so let's look at this box. It's kind of confusing, so I want to talk you kind of through it here. So after 0 years, I have $10,000. What do I do to get my new balance after year 1? Right, I multiply the initial value by 1.05 just a single time, right? So after the second year, in total, how many times do I have to multiply by 1.05? Twice. Once after the first year, once after the second year. After the third year, how many times have I multiplied by 1.05? 3 times. Once after the first year, once after the second year, once after the third year, right? So I take my initial value. This is how we avoid filling out the box and doing it over and over and over again and being real boring, okay? So $10,000. And then I need to multiply by 1.05 how many times after the third year? 3 times. So instead of putting times 1.05 times 1.05 times 1.05, how can I do that differently? Times 1.05 to the third power. Okay, because I'm multiplying by 1.05 3 times. So after the fourth year, I have my initial value, 10,000. And then how many times do I multiply by 1.05 now? 4 times. For the fifth year, 10,000 times 1.05 to the fifth power, because now I'm multiplying it by 5 times, right? Each year I multiply by 1.05 another time, so my exponent is increasing, okay? All right, so arming yourself with that knowledge, I want you guys to answer 7 and all of 8 together with your partners. 7 and all of 8 together with your partners. Go ahead. All right, so writing my expression for year 8. Let's kind of remind ourselves about the structure of every exponential function, okay? Because we're not always going to have this nice little leading box that helps us write our equations. So what's the number out front?
Initial
It's the initial value. And in our case, our initial investment is $10,000 times the growth factor or the constant factor, which what are we multiplying by each time here? 1.05. 1 for our initial value, 0.05 for the interest, to the time power, and the time here is year 8, so to the 8th power. Okay, if I wanted to represent that with an with a variable in there, just so it shows me in any year after t years, so just in general, I have my initial value times 1.05 to the t power. Make sure it's an exponent. It's not just 1.05t. Okay, it's 1.05 to the t power. That makes it exponential because there's a variable in the exponent. Okay. Then if I wanted to confirm for t equals 6, I could plug 6 in for t, calculate that. We've practiced that last class, so I'm not going to worry about it. Okay? All right, so now we're going to skip a whole bunch of stuff. Okay? So skip to the back page. And also skip 16. We're going on to 17. Okay? So we're skipping a bunch here, going on to 17. So 17 says, or right above 17, it says, at the same time that Madison, we skipped over Frank, so we don't need to worry about Frank. At the same time that Madison opened her account, another friend, Casey, opens a savings account in a different bank. Casey deposits $12,000, so that's a little more than Madison, and her interest rate is 4%. Madison's was 5%, hers is 4%. So go ahead on 17, I want you to write the new function for Casey, and then try to discuss 18. And at the bottom where it says, justify using a table graph or both, skip that part because we're going to look at it with a graphing calculator in a minute. Okay? So write the function for 17 for Casey, and then just kind of start discussing if you think what Casey thinks is right or wrong on 18. So go ahead. Okay, so what do you guys think about 17? It gives me the function name. So for Casey, we're going to name it K of t. What is the initial value in the beginning of Casey's function? 12,000. So that's a little bit different than Madison's. Times, what's the growth factor for this function?
1.04.
So we still need the 1, right? Because we are increasing the value. So it's got to be bigger than 1. And her interest rate is 4%. So I heard all you guys say 1.04. That's good. To the t power. Okay, what about her claim? She says Casey believes that since she started with more money than Madison, she will always have more money than Madison. What do you guys think?
No.
What do you think, David?
No, because eventually over time, since her number's lower, it just, well,
What number's lower?
the interest rate's lower.
The interest rate. So you think since Madison's interest rate is 1% higher, eventually she will catch her?
Yes.
Okay.
Yeah, it'll take a long
It
time.
doesn't matter.
Okay, so it might take a while, so that may be something we have to take into consideration. Just curious, how long do you think it will take for Casey or for Madison's to catch Casey?
5 months.
500 years?
100.
Oh, 100 years?
5 months. Good 5 months.
Do I have a different guess than 100 years?
5 months.
50 years.
5 months? Talking $2,000 difference. What? 12 years? Or months? 12 years?
12 months.
2.57 years.
We'll see.
15 years.
2.5.